Okay, well, let's get started. Today, we're very pleased to have Alex Miquel talking to us about implicative algebras, a new foundation for realizability and forcing. The floor is yours, Alex.
Okay, thank you very much for the invitation. So now I'm talking to you from summer. As you can see, I'm completely burnt already. It's summer in Uruguay. I'm French living in Uruguay. Okay, and now I will start with the serious stuff. And my aim is basically to merge some well-known notions of models. Okay, so start with Tarski models that we all know. But very quickly after the design of Tarski models, Kliny designed what is called intuitionistic realizability. That was not only a model for probability of intuitionistic logic, but also a model for proofs, because you are not only interpreting provable formulas, but you are also interpreting proofs themselves as programs. And one of the problems of Kliny realizability that it was definitely incompatible with classical logic. But in a completely independent way, you also have the technique of forcing designed by Cohen and its equivalent thing, which are Boolean valued models. So we have lots of notions of models, and just to make the thing more complex or more complicated, from the 90s, Krivine introduced classical realizability that interprets classical proofs, and that is actually a generalization of Tarski models and of forcing. So now if we look at the full pictures, on the left-hand side, you have the forcing side, and on the right-hand side of the picture, you have the realizability side. The forcing side is quite obvious because basically you interpret conjunction as meet. Okay, so conjunction is the same as a meet, is the same as a universal quantification. Universal quantification is just an infinitary conjunction. And here you have Heyting valued models that contain Boolean valued models, and inside you have Tarski models. But when you go to the realizability side, things are much more complex because basically you distinguish universal quantification from conjunction. Conjunction is now a Cartesian product, whereas universal quantification keeps being uniform. That is, it's still a meet, it's still some kind of an intersection. And to make things more complex, intuitionistic realizability actually contains Tarski models as a very degenerate case when you have a one-point PCA. But on the other hand, classical realizability has no intersection, almost no intersection at all with intuitionistic realizability. So you have a picture way more complex. So all my problem was how to interpret that, how to merge all of these traditions together. So, and for that, we shall go to categorical logic. So I will not recall categorical logic, the basic of categorical logic. But basically, I will concentrate my attention to the notion of tripos. I will almost not speak about toposes because we know that to build topos from logic, we just need to build a tripos. And the problem that for a long time, people knew that actually if you are doing realizability with PCAs, it's completely incompatible with classical logic. That is, there is a theorem saying that if you have a topos induced by a PCA that is classical, it's if and only if the PCA is degenerated, okay, has one point. And on the other hand, Krivine ignored completely that tradition and decided to do what is classical realizability. So the problem is how to make all these things to fit in the same picture. So now let's start from the beginning. Historically, when people were designing toposes from logic, they were using either toposes, forcing toposes, or localic toposes coming from complete Heyting algebras or complete Boolean algebras, or they were using realizability. And of course, the problem is that you have a lot of arrows. You can also go to this side to go from the side of algebraic structures to toposes, but you can also use these same structures to make models of set theory. So basically, you have models of Boolean valued models of set theory, Heyting values models of intuitionistic set theory, but you also have realizability models of set theory. And of course, everybody wanted to factorize this construction. everybody wanted to find the grail, the holy grail of this thing, to find a structure that would subsume everything, but they never completely succeeded because they got a higher order structure, which is also of tripos. So tripos is just a functor. It's it's a categorical model of higher order logic. This is the way I see it. And basically, it's a higher order structure. So it's not exactly an algebraic structure. It's very, very high. It's much closer to the topos we want than to the algebraic structures we have here. So, and fourth, of course, to make the thing more complex, Krivine in the 90s defined what are called abstract Krivine structures and showed how to make classical realizability in Zablow-Frankel. So the problem was how to make this arrow fit. And the first work in this direction was done by Thomas Streicher, who showed that basically when you have a Krivine structure, you can turn it easily into an ordered combinatorial algebra with filter, and using the same technique as you use with PCAs, you can build a tripos and then you get a topos. So it was the first step to say, okay, actually classical realizability fits in the framework of categorical realizability. But for me, the situation was not satisfying enough. And that's the reason why I'm introducing implicative algebras as the second order object that is needed to factorize all these constructions. So we are much more level. And actually, we shall see that in some sense, implicative algebras are equivalent to triposes. So that's basically the picture I will tell today. That is how to unify all the different forms of realizability enforcing with a suitable algebraic structure. So basically, I want to encompass complete Heyting algebras, complete Boolean algebras, partial combinatorial algebras, ordered combinatorial algebras, abstract Krivine structures, and so on and so forth. And here I will discuss how we can build categorical models from implicative algebras. And I will leave aside the problem of making models of intuitionistic and classical field theory, but actually implicative algebras can be used for that too. And I have to cite a lot of people. This work has many sources of inspiration. So basically, there was almost the structure was almost appearing in the PhD of Frédéric Ruyer in 2007, and many ideas are borrowed from Thomas Streicher. Okay, so now I will make a basic crash course presentation of what is an implicative algebra, and for that I start with implicative structure. So an implicative structure is just a triple formed by a complete mid-semi lattice. Here you have just a mid-semi lattice of truth values or of types. You can think of its elements as types or truth values. And basically here the ordering, the most simple way to understand it, it's not implication, it's the ordering of subtyping. And here that's the most important thing. Here I will show that subtyping is something much more primitive than what we think usually. And then you have binary operation of implication, which is just something that is anti-monotonic on the left-hand side, monotonic on the right-hand side, and that fulfills this very strange distributive rule. Okay, basically it commutes on the right-hand side with means. So since it's a complete lattice, I use bottom and top. And if you use axiom 2b, we see that in particular, R arrow top is equal to top for any truth value A. Okay, so that's basically the definition of what is an implicative structure. And you have many implicative structures in the real life. The first and most obvious example, each complete Heyting algebra is an implicative structure whose implication is derived from the ordering. Here, that's very important to understand that in this definition, we have two components that are quite independent, the ordering and the implication, because ordering is subtyping, implication is an operator that transforms two truth values into a single truth value. And of course, in the case of complete Heyting algebras, implication is deduced from the ordering using Heyting's adjunction. Of course, if you take a total combinatorial algebra, you can take the power set of your set of programs, you define subtyping as inclusion, you take as the arrow Kleini's implication, very standard construction, and then you get what is an implicative structure for free. And if you do that with a partial combinatorial algebra, you just get what I call a quasi-implicative structure, where only this equation is lost. But there are lots of completion theorems which say that each time you lose this equation, you can recover it in a larger implicative structure. So, and we can do similar construction for ordered combinatorial algebras. But it also works with Krivine structures. So it's very fun with Krivine structures because Krivine realizability is not oriented toward truth values, but towards falsity values. So now you take the point of view of the opponent. Your elements are just set of stacks. So pi is a set of all stacks. Now subtyping is reverse inclusion between sets of stacks, because now we think in terms of falsity. And here you have basically the definition of the arrow is just Krivine's implication. And it's another implicative structure. Okay, so basically what I'm showing here is that the basic components from which we build realizability or forcing are all particular cases of implicative structures. So now the manifesto, I have to explain ideas. There are important ideas underlying here. So primarily, the elements of implicative structures, they are to be thought of truth values. But the big surprise is that this structure is so rich that you can encode lambda abstraction and application at the level of truth values. So in particular, thanks to this, you can see each realizer as a particular truth value, but you can also see each truth value as a generalized realizer. So basically, the main feature of this structure is to get what I call the ultimate Carry-Howard identification. Realizer equals program equals formula equals type. So I'm very proud of that when I saw that, because I thought that we needed to unify the four forces in some sense. Okay, so now what is the meaning of ordering? Here is intentional ordering as opposed to extensional ordering. So here, primarily, if you think A and B as truth values, deordering means A is a subtype of B. So it's some kind of direct implication. Subtyping is just says that A implies B without changing your proof. The identity is just a proof of A implies B. But if you now see A as a type, if you see A as a realizer and B as a truth value, it also means that A has type B or A realizes B. The same relationship is used to express subtyping, but also typing. But if you now see both A and B as realizers, it also means that A is more defined than B. That is, it's the same ordering that will express subtyping, typing, and actually reverse Scott ordering. Okay, reverse definitional ordering. That was a big surprise when I designed this structure. That is, initially I wanted to make something like types, and then I wanted to add proofs, and then I discovered that proofs were already inside. Okay, I will show that. Okay, I take any implicative structure, and believe me or not, but here in this structure, you can define the following meets because you have a complete lattice. And here is a perfect definition of application. And here, if f is an arbitrary function from A to A, then you can define lambda f as an element of A. Okay, and now the properties are the following. First, these two constructions are monotonic. Okay, then you have the beta reduction rule, which says that if you apply the truth value lambda f to some A, it's below less, it's a subtype of f of A, which is exactly beta reduction. You have eta expansion. So eta goes into the other side, other way, something we are expecting to in general. And the important point is the fundamental adjunction of implicative algebras. That is an adjunction not between conjunction and implication, but an adjunction between application and implication. The main difference is that here the ordering is not the logical ordering, but it's subtyping. And with respect to subtyping, saying that A is below B over C is the same as saying that A applies to B is below C, is a subtype of C. So it's a new adjunction. And my claim is that this is the adjunction that is underlying logic. and from which we can rediscover the higher level adjunction with implication. I will describe all of that. Basically, implicative structures are the intentional side of logic. So once we have application and abstraction, we can encode all lambda terms in this structure. So basically, you can associate to each lambda terms t with parameters in A. You can associate a truth value t up to the A that is defined as expected. That is, you define each parameter is translated as itself. The syntactic lambda abstraction is translated as a semantic lambda abstraction. And application, syntactic application is translated as the application I defined in the former slide. And what you get is that beta reductions, when you beta reduce, then you go upwards in your structure, or if you prefer, you become less defined. If you look at this in the Scott ordering style, and eta goes the other way around. Here, there is an important point. This is not a denotational model of the lambda calculus because this map is not injective in general, even on beta eta normal forms. I have a lot of examples in which this map might be degenerated or non-degenerated, and sometimes strange phenomenon will appear. So it's much richer than the usual denotational models of lambda calculus we have.
Sorry, Alex, what is this double-headed arrow T?
It's a ground step beta reduction. It's just been many steps of beta reduction, many steps of eta reduction. Thanks.
Thanks.
And so here it's really, you can see that it's an algebra of truth values in which I can encode lambda terms. So it's very nice for having proofs inside. And basically, but it's not a model, it's something else. So now there are very impressive properties of implicative structures. Now, since we have both truth values and lambda terms inside, we can compare them. So for instance, if you compile the identity in A, which is just how to interpret, you will observe that it's the same as its principal type. That is, here you can see here this thing as lambda A, or as the type for all A implies A. Here they are one and the same thing. That is, the polymorphic identity, the identity and its polymorphic type are the same. The same holds for K, and the big surprise when I was doing that was to discover that actually if I also compile the combinator S, it's exactly equal to its type. So here, that's the advantage of having structure, having types and terms at the same level. Then we can perform some interesting identifications. And here we can understand that it's the principal type because we cannot insert anything in between. Okay, and we have similar equalities for the combinator C and W. By analogy, I will define CoLCC. Okay, I define CoLCC as the law of Peirce. It's just a definition. Using that, I believe that each object is equal, the important combinators are equal to their principal types, and I have no way to compile CoLCC using lambda terms because it goes outside the lambda calculus. I use the identification with the law of Peirce, and here I have CoLCC inside my structure for free. However, it seems nice, but not completely. Before that, I will just tackle a particular case, the case where my implicative structure is a complete Heyting algebra. So recall that a complete Heyting or Boolean algebra are the particular case where implication is defined this way from the ordering. And when you are in this particular case, it turns out that application merges with meets. It just amounts to the meets, okay? That is, and now you understand the former adjunction, because if application amounts to meet, then you recover the usual adjunction between meet and implication. Also, if you compile any lambda term in a complete Heyting algebra, all the pure lambda terms collapse to top, which explains why, in general, when we work with complete Heyting algebras, we are not interested in lambda terms. We are not interested in proof because they are all equal. And moreover, if A is a Boolean algebra, then a complete Boolean algebra, then CoLCC also collapses to top.
Sorry, Alex,
So
another question. What is this?
Yeah.
I keep not quite hearing the word that CC is referring to.
Call CC is just the primitive that is used in classical realizability to interpret the law of Peirce. It's just a programming language device. Basically, it's a capture the current continuation. It's an operator that has been shown to realize the law of Peirce by Krivine in 1990, and that's the main device of classical realizability.
Great, thank you.
So CC is called CC, call with current continuation, and you can see it as the genuine proof of the law of Peirce. Okay, so basically it explains why in forcing we do not interpret lambda terms because they all collapse to top, and when we are in classical forcing, we do not interpret classical logic in a non-trivial, it's completely trivial. Okay, but now there is a warning. The warning is not, it seems to be very nice, this picture, because you have lambda terms everywhere from the beginning. But sometimes it might be the case that if you take a dummy implicative algebra, an implicative structure that is quite weak, you will get the fact that compiling a particular lambda terms, you will get top. Intuitively, this means that in the logic induced by this particular implicative structure, this lambda term is inconsistent. That will be typically the case in classical and intuitionistic realizability. If you interpret some classical reasoning, call CC, you will get bottom because it's inconsistent. So the thing is that actually there are a lot of implicative structures with very weak logics in which the compiling of lambda terms gives you top bottom, just saying that this lambda terms, I cannot represent it. Okay, so I say that an implicative structure is intuitionistically consistent when the denotation of lambda terms is never equal to bottom, and classically consistent when the same holds with closed lambda terms with call CC. Here, I use the fact that we can always see classical logic as intuitionistic logic plus the law of Peirce. If you add the law of Peirce to intuitionistic logic, you get full classical logic. So there are lots of examples of, if you take any non-degenerated complete Heyting algebra, Boolean algebra, if you take combinatorial algebras, OCAs, they are all consistent, intuitionistically consistent. And if moreover you take Krivine realizability, it's classically consistent. Okay, so now we have basically the notion of truth values, but we also need a notion of truth. And for that, we need to go to the next topic, which is the topic of separations. So in Boolean algebras, Heyting algebras, to distinguish between the truth and the false, in general, you introduce a filter. The filter is just a criterion of truth in a Boolean algebra or in a Heyting algebra. Because the word filter was taken, I did choose the word separator. Okay. So I define, now take an implicative structure, okay, you have an implicative structure here, and I call a separator of A is just a subset that is almost like a filter. So it should be upwards closed with respect to subtyping. So this is a criterion we know for a long time for filters. It should contain both combinators K and S. So here, it should be stable by modus ponens. That is, if A implies B belongs to S and A belongs to S, then B belongs to S. And then we say that a separator S is consistent or classical when it's consistent when it does not contain bottom, and it's classical when it contains call CC or the law of Peirce, if you prefer. Some observation. Here I put this stability condition with respect to modus ponens because I see elements of A as truth values. So I prefer implication. That's a primitive object. But equivalently, I could have said that it's closed under binary application. And below, under the criterion, the condition 1, that is, if I have a subset that is upwards closed, condition 3 is exactly equivalent to condition 3 prime, which says that we are closed under binary application. That's a good news. And the important point is that in general, separators are not closed under binary means, and that's the reason I do not call them filters. That's very important to change the word. In realizability, I don't know why, many people call filter things that are not closed under binary means, and for me, it's almost a crime. The important point is that we should always distinguish the ordering of subtyping with the ordering of implication, which I will introduce in a few slides. Okay, so the intuition is that a separator is a criterion of truth, and with the same implicative structure, you may have several criteria of truth. So in the particular case where A is a complete Heyting or complete Boolean algebra, a separator is exactly the same as a filter. That's a good surprise. That is, if you are working in the field of Heyting Boolean algebras, no difference between separators and filters. That's one and the same thing. But in general, separators are not filters because they are not closed under binary means. They are closed under application, they are closed under modus ponens. They contain basically the Hilbert's axioms, but they are not filters. So each time you have an intuitionistic, you have an applicative structure, you can define two separators. You can define the smallest possible separator, which I call the intuitionistic core. And you can also define the smallest separator containing core CC, which I call the classical core. There are the two fundamental separators, they are the smallest ones. But you are free to change your separator if you want. And here, of course, where we have complete Heyting algebras and complete Boolean algebras, the intuitionistic and classical cores are completely trivial. Okay, the idea is really to have the same theory for forcing and realizability and to see the same concept instantiating in different ways in the different frameworks. Now, separators, they are not filters, but they can be used the same way as filters. First, they are closed under lambda constructions, which means that if you take a term and a lambda term and you fulfill its three variables with parameters in the separator, then the compiled lambda term itself remains in the separator. Basically, separators are stable under all intuitionistic proof theoretic constructions. Okay, that is, you have all the lambda terms inside. The lambda terms are in all the separators. Actually, you can define the separator generated by an arbitrary subset. So sep of x is the smallest separator containing x as a subset. Is the same thing as taking all the lambda terms generated by this set of parameters and then taking the cross closure. In particular, the intuitionistic core is the separator generated by the empty set. The classical core is the separator generated by call CC. And you even have a semantic deduction lemma saying that the implication belongs to the separator generated by X if and only if B belongs to the separator generated by X union A. That is, you put A into your context. Very useful for doing proofs to have this kind of semantic deduction lemma. And exactly the same way as we define ultra filters, we can define ultra separators as the maximal consistent separators. And in particular, of course, every consistent separator can be extended into an ultra separator. The ultra separator axiom has exactly the same strength. Actually, it's equivalent to the ultra filter axioms. So from point of view of logic, it's much weaker than the axiom of choice, but that's important to mention it. And of course, an ultra separator is a separator whose induced Heyting algebra is equal to 2. But I will come back to this point later. I think I skipped some slide. No, okay, I didn't skip it. We shall come back to this point later. Okay, now we can first interpret first order logic. So if you want to interpret first order logic, here you interpret implication as the implication, negation as a row top, bottom. And then for interpreting conjunction, disjunction, you use the usual second order encodings. Because we have a second order structure, we have all meets, all joins, we can use the basic encodings that are the usual encodings of second order logic. Okay, for conjunction, disjunction, here universal quantification is just infinitary meet, And existential quantification is just the second order encoding of existential quantification. So some people criticize this structure to say that it's basically called by name because it gives all the privileges to the universal quantification and make existential quantification complex. And there is no way to have both sides simple.
What was M again?
Yes?
What was M in the bottom line?
M is the model in which we interpret your logic. Basically, it's like a Tarski model. When you want to interpret a first order theory, you have a basic set. M is the domain of quantification.
Okay.
Okay. So, of course, you have a theorem of soundness saying that if some formula phi holds in intuitionistic logic, then its denotation will belong to the intuitionistic core, that is to the smallest separator of A. And the same for classical reasoning. Okay, now I have to define what is an implicative algebra. Because before I define what is an implicative structures, that is a set of truth values with implication and subtyping. Now I define an implicative algebra as an implicative structure plus a separator. That is, you just add to your implicative structure a fixed criterion of truth. Okay. And once you have that, you can define entailment. You say that a truth value A entails another truth value B modulo the separator S, whenever the implication A implies B is intuitively true, that is, belongs to S. And here, this thing is a pre-order, and if you make the post-set reflection, then you get actually a Heyting algebra. Okay. That is, it's the extensional collapse of your implicative structure. Your implicative algebra represents intentional things with subtyping, a row. It has its criterion of truth. Okay. Okay. But once you make the quotient, that is A divided by S, it's just a post-set reflection of your A with this new pre-order, then you get the Heyting algebra, which is basically the extensional collapse of your object. Okay, that is the underlying logic. Now you have identified all the truth values that are probably equivalent modulo your separator S. And of course, if your separator was classical, then you get a Boolean algebra. The observation is that this induced Heyting algebras is in general not complete. It's much closer to what we know to be a Lindenbaum algebra. Okay, so now some observation about non-determinism and filters. So recall that in the theory of implicative algebras, separators, they play the same roles as filters in the theory of Heyting algebras. But in general, they are not filters. However, if you give yourself any implicative structures, you can always define the following two values. What I call the non-deterministic choice operator, is very strange, that basically that you can think of it as a lambda terms that non-deterministically reduces to its both arguments. Basically, fork, I call it fork, some people call it flip. Flip applies to A and B. Intuitively is a subtype of both A and B. It means that intuitively reduces to both A and B. And here you have a very small variant that is a parallel OR. And here you can observe that a separator is a filter if and only if it contains the non-deterministic choice operator. So that's very strange. That is, sometimes separators are degenerated and they turn out to be closed under meets, and for that, just need to check that this object belongs to your separator. And the same, if you have a classical separator, you only need to check the presence of this object that is much weaker. Now, you can characterize the situation of difference between forcing and realizability from this theorem. So the following is, if you give yourself any separator, A, S, the following are equivalent. S is finitely generated and contains the non-deterministic choice operator. it's the same as saying that S is a principal filter, which is very strong because it's generated by a unique proof, theta, and the universal proof of S, and is the same as saying that the induced Heyting algebra is complete. That is, when you make the quotient, you get a complete Heyting algebra, and the canonical surjection commutes with infinitary means. And in model theoretic terms, I will come back to this later, this situation corresponds to a collapse of intuitionistic or classical realizability into Kripke or Cohen forcing. That is basically, now the idea is that forcing is just the non-deterministic version of realizability. If you take realizability, you add inside a non-deterministic choice operator, you get something, your separator starts to be closed under meets, then you show that it becomes a principal filter, and then you are done. What you are doing is not realizability anymore, but you are doing forcing. The typical example, if you take Barbanera and Berardi symmetric lambda calculus, which was a calculus introduced in the end of the 90s, 96, I think. This calculus, if you make a realizability model with this calculus, since this calculus contains non-deterministic choice operator, because it's non-deterministic, you can show that this calculus, the realizability model, is no more than a forcing model with a very complex presentation and a fake computational presentation. That's very interesting to see that sometimes we want to add a feature to our calculus, but actually we collapse too many things. So now let's go back to the tripos, the implicative tripos, and I will conclude on that. So now I take an implicative algebra. Given any set I of indexes, because I want to index now my implicative algebras by set, I observe that I can always take my implicative algebra up to the I, or I get A to the I, the ordering up to the I, everything defined component-wise, and it's still an implicative structure, which I call the power implicative structure. Here, I put aside the separator because I will give to it a completely different treatment. Now, I could do the same for the separator, but in this case, I would get something completely uninteresting and boring. What I will do is that I will, instead of taking S to the I will take S bracket I, which is basically the separator generated by constant families. Basically, I want that in the separator, in this power structure, I want to take the separator generated by constant families of objects of S. So now I can associate to each index I the power implicative structure up to the I, quotiented by the uniform power separator induced by I. And since this is an implicative structure, and since this is, and since this is a separator, the quotient is an induced Heyting algebra. However, it's much more because the correspondence is a functor, it's contravariant functor, and it's actually a tripos. And that's the implicative tripos induced by the implicative algebra. So here, in one slide, you have the full construction of the implicative tripos induced by an implicative algebra. Now, the observation is that this construction actually encompasses almost all well-known triposes. Basically, if you do the same with an implicative algebras coming from a complete Heyting algebra, you will get the usual tripos construction. The same holds if you take a total combinatorial algebra, and you can also do the same with partial combinatorial algebras, but you need some completion trick I will not describe. And you can also do the same with abstract Krivine structures. Okay, so basically, the former construction, the one of this slide, factorizes all the well-known logical constructions of triposes in the literature. That is, they are all instances of this construction. Now, of course, as for any tripos, each time you have an implicative tripos, you can turn it into a topos via the standard tripos to topos constructions. I will not discuss anymore on toposes because I'm focusing on triposes. So now the question is that what do implicative triposes bring new with respect to forcing triposes, intuitionistic realizability triposes, and classical realizability triposes? First, we can characterize forcing triposes. So let's take an implicative tripose, that is a tripose induced by some implicative algebra. Then the following are equivalent. The tripose P is isomorphic to a forcing tripose if and only if the separator S is a principal filter of A, and if and only if the separator S is finitely generated and contains the non-deterministic choice operator. That is basically this theorem that captures both realizability and forcing, says that up to isomorphism, forcing is the same as non-deterministic realizability. Okay, that's a theorem basically putting everything in the same picture. Now, the big surprise too, that actually if you have a tripose that is induced by classical implicative algebra, it's isomorphic to a tripose induced by Krivine realizability. On some sense, implicative algebras on the classical side bring nothing new with respect to Krivine realizability. It's just another way to express the same thing. Okay, they are equivalent. I will come back to this later because it's very important, this result. Okay, now I will finish this section about implicative triposes with some completeness results. So we have seen that implicative triposes encompass a lot of well-known triposes, but do they encompass all triposes? And the surprising answer is yes, actually, you can show that each set-based tripose is isomorphic to an implicative tripose. So basically, we capture all the triposes. And from the point of view of foundations, this theorem expresses that that a tripose, okay, there is a big typo here, sorry. Basically a tripose, a single tripose that is a structured proper class can always be described by a single implicative algebra that is a structured set. You have a big reduction of complexity here. And it explains, of course, a fortiori why we succeeded to turn all the well-known triposes into implicative triposes. But also, since implicative algebras have the same expressiveness as ordered combinatorial algebras, with filters, the completeness theorem also holds for the latter. That is, actually, you can show that any tripose can be derived from an ordered combinatorial algebra with a filter. So basically, the picture was the following, and you have now back arrows saying that any tripose can be presented as an implicative algebra, and actually you can see implicative algebras as particular cases of ordered combinatorial algebras with filters. Okay, so now we have, I think, a much more clear picture of the difference between forcing and realizability. The interesting point is that, of course, going from this side to this side is just the extensional collapse, and going from this side to this side is just a way to reveal the intentional contents, but it uses a lot of axiom of choice. So this red arrow, the proof requires a lot of axiom of choice, because it's not canonical, this construction. This construction from implicative algebras for typoses is functorial. The other way around is not functorial due to the axiom of choice. So, okay, but you also have first order completeness, because you can also define, I showed it a glimpse of that. You can define a notion of a model for any first order language. Basically, it's the same as Boolean valued model of a first order theory, but you replace your Boolean valued algebra by an implicative algebra. And the rest of the interpretation goes the same. And an implicative model is just an A model for some implicative algebra for some first order theory. And of course, you have the usual soundness theorem, but the important theorem here is the strong completeness theorem, which says basically that each classical first order theory is captured by a particular implicative model. That is, for each first order theory, you can find an implicative model that captures exactly the provable sentences of your theory. nothing more, nothing less. It's much stronger than usual completeness, because instead of saying, okay, I take the intersection of all the theories induced by all the models, I have a single model that captures everything. Actually, I should mention that this strong completeness theorem already holds for Boolean valued models, but the proof relies on the completeness theorem of first-order logic. Consequence: if you take a consistent classical first-order theory, from the strong completeness theorem, there is a full implicative model that captures the theory. That is, you have T proves phi if and only phi is satisfied by M. Okay? But if you have, since this theory is consistent, the underlying separator of this implicative algebra, the one underlying the implicative model, is consistent too. So you can extend it into an ultra separator. Okay, so if you pick some ultra separator, you just turn your implicative model into a Tarski model, and you get back the usual proof of completeness of first-order logic. That's important because the strong completeness theorem does not, the proof of the strong completeness theorem does not rely on the first-order completeness theorem, the usual completeness. So it's just a new reading of the first-order completeness, which says that basically, when you want to turn a consistent first-order theory into a Tarski model, there is an intermediate step, which is the notion of implicative model, in which you don't lose anything. You capture exactly probability. And then if you want to go to a Tarski model, then you need to increase your notion of truth. So you extend your separator into an ultra separator, and then you get the expected desired Tarski model. And note that the first equivalence is constructive. The second one uses the ultra filter axiom and is not constructive. So it's another way to read back the usual completeness theorem of first-order logic. So now I think it's time to conclude. So just to conclude, implicative algebra, I hoped, at least I tried to convince you that it's just an algebraic structure to factorize the model theoretic constructions underlying forcing and realizability. And basically, the main idea is that we can always work with truth values as if they were generalized realizers. That is, realizers and truth values are on the same level, and that make them much easier to work with. We have seen that each implicative algebra induces an implicative tripos, and this correspondence is surjective up to isomorphism. That is, any tripos is isomorphic to some implicative tripos, but it's very far from being unique, because of course you have several intentional sides that go to the same extensional side, a well-known phenomenon in logic. In this structure, you can just see forcing as non-deterministic realizability. So for me, it was the most enlightening thing to understand that forcing is just some kind of commutative or non-deterministic realizability. And the other way around, you can see realizability as some kind of non-commutative forcing. And in this structure, basically, when you are doing classical implicative models, it's exactly the same as doing Krivine realizability. And since we know that all triposes are implicative, we just composing both theorems, we know that actually every classical tripos comes from Krivine realizability, which is really a nice reduction to classify the triposes. So now I will conclude on some ongoing work. So now, since actually I published it in 2020, the paper, but I had copies circulating from many years before. So a lot of people have worked on that. My PhD student, so Miquel is not a typo, Miquel is another guy, is my former PhD student. We just have a last name differing from one letter, but it's sufficient to distinguish both of us. So he designed conjunctive and disjunctive algebras for interpreting call by name and call by value in realizability. And more recently, with Cohen and Tate, they designed what they call evidence frames, which is a way to incorporate more computational features inside realizability. And some ongoing question is just to study the category of implicative algebras and to study the possible notions of morphisms. That's a big work because now we have lots of candidates for being a morphism of implicative algebras, and we still don't know clearly what is the correct notion. And of course, another ongoing work is the designing implicative models of intuitionistic or classical Zermelo-Frankel set theory using these implicative structures. So that's all what I wanted to say. Thank you very much.
Thank you. Lots of claps in the chat there. If anyone has a question, you can raise your hand or just unmute yourself.
I have a question about 2 points that you made concerning when you have a tripos, you can get implicative algebras. One was that this simplifies things because you get down to small. The implicative algebra is small compared to the tripos.
Yeah.
The other is, unfortunately, that it's not canonical. You need the axiom of choice. And I wonder whether there's a trade-off here. If you were to allow something analogous to implicative algebras, but large, class-size things, would there then be a canonical example?
Actually, it's a good question. Many people have complained about the non-canonical thing. So you are just one person more, and I have definitely no idea on that. My intuition is that there are good reasons that it's non-canonical, because I consider that several programming languages should be able to induce the same logic. But perhaps I'm mistaken, but I have no idea. But I know that a lot of people complain about that point. So basically, it means that you tend to see the non-canonical things as a bug, whereas I see it as a feature.
Well, I wouldn't say that the canonical thing should be the right intentional view of some extensional thing, but that there should be a particular view which is canonically definable, and then there are a bunch of others. So maybe the least or the greatest or something intentional picture. Maybe I should add of proper classes here. I'm thinking of what may be a completely silly analogy, but if you take a topos, it comes from, say, a Grothendieck topos is defined from some site, but there are many, many sites. The site is usually smaller than the topos, but it doesn't come canonically from the topos. But you can get something canonical by taking the topos itself as a site with canonical topology on it. That is probably not what you would want as the natural site of definition, but it is a canonical one.
Okay.
The penalty for canonicity is that it's large.
Let me improvise something. Okay, you have your tripos. You have a bunch of implicative algebras that represent your tripos. Make the full product of them. Take the product. It's no more a set, it becomes a class. Perhaps it's what you want.
Okay.
This construction is actually quite useful because it works for Boolean valued models, for instance.
Well, thank you, Andreas. We have time for another question, if anyone has one.
I have one, but I should let somebody else go first if anybody else has another question.
Oh, why don't you go for it?
Okay. This is, again, rather speculative, but there are, of course, connections between these various intuitionistic and classical and so on models. I'm thinking in particular of something like the double negation translation of classical logic into intuitionistic logic, which has a nice picture. You know, in a topos, you have the double negation topology, you take its sheaves and everything is wonderful. Is there something like that in implicative outcome? And bring that down. How far down in the picture does it go?
Yeah, actually, but not on the side of implicative algebras, on the side of conjunctive and disjunctive algebras. And that's one of the reasons why I made work by students on this alternative presentation of conjunctive and disjunctive algebras. And in this framework, you can easily define the notion of double negation translation, and it works quite well. I don't remember the details, but I think that you should go to this thing. That is, the answer should be there.
Okay, good. Thank you.
Okay, great. Well, if there are no other questions, let's thank Alex again. So thank you.
You're welcome.
And we'll stop the recording.